Hi, the Coarea formula is stated again here for your convenience in blue. In previous videos we saw that it is enough to prove the apparently simpler case of applying to G equal to characteristic function of a measurable set, and in that case the Coarea formula reads as the formula you see on the screen. From the definition of the Coarea factor as this determinant, it vanishes exactly when the rank of the derivative is strictly less than n. Therefore, if A is a subset of Rm that is measurable and rank of the derivative of f of x is strictly less than n at almost every x in A, then the left hand side is 0 because you integrate 0. Therefore, the right hand side must also be 0. Minus n f inverse of z intersected with A, the ln of z must be 0. So this must be proven for the critical set of the function f. So critical set of the function f in our context will be x is in the domain where rank of the derivative of f at x is strictly less than n. So we can take A equal to this critical set. So this will be our goal in this video, and we will talk about other issues connected to that. The question of just how big the image of a critical set is a very fundamental one and has been investigated early on. So how big can f of CF be? Well, CF itself can be all of Rm. Take the constant map, for instance. So we cannot really control how big the CF is. But maybe we can somehow control its image, because the function f is degenerate in some sense along CF, so maybe its image shouldn't be too big. And that was confirmed by Morse in special cases and then Sard. So the famous theorem called Morse-Sard, it's in 40s if I'm not wrong. It says that if f from Rm into Rn, so this is for all m and n, we don't really need to have m bigger than or equal to n, but actually when you map into larger space, it's actually simpler theorem with simpler proof. So I stick to our context of m bigger than or equal to n, but again, remember that this is not really necessary in the full statement of the Morse-Sard. So if this function f is ck, k times continuously differentiable, where k is at least equal to 1 plus m minus n, then the Lebesgue measure of the image of the critical set is 0. And that's a spectacular result there, that the Lebesgue measure of the image of critical set is 0. So in particular, this says that for Ln almost every z in Rn, the set preimage of z intersected with this critical set is empty. It's just immediate from that first part. So that the preimage of a point, a generic point, does not even intersect with the critical set. So there are a very important corollary of this. By the way, this Morse-Sard is also true for maps between manifolds by easy manifold tricks. So one main significance of this is for Ln almost every z in Rn, F inverse of z is an m minus n dimensional manifold, CK manifold, as regular as the function f. Proof is just one word, well, one phrase, implicit function theorem, and we've extensively talked about this in a separate video, because in this particular case, because we talked about Lipschitz implicit function theorem, but for a regular one, since the preimage does not at all intersect the critical set, at every point the implicit function theorem applies to give the fiber the level set as the zero set of a regular CK regular function. And locally you get that it is a manifold, and that's it. The corollary that will be more relevant to us is that if A is a subset of the critical set, which is another way of saying that rank of the derivative is less than n almost everywhere on A, well, in this case almost everywhere is everywhere because the derivative is continuous, then this integral Rn hm minus n f inverse of z intersected with Cf dln of z equals 0. And well, proof is that the integrand is 0 for every z that is not in f of the critical set, because this set is actually empty set, so its Hausdorff measure is 0. So this is kind of in a trivial way this integral equation holds. I must mention that f inverse z, although a manifold, can be disconnected. There is nothing to prevent it from being disconnected. All of this agrees with the pictures I showed you in my beginning videos, where I would move the image value and then you would see the picture of the level sets. And there would be exceptional points when I passed through them, I would cease to be a manifold, but otherwise I was a manifold, which agrees with this Morse-Sard theorem, because if I pick a random point, there is probability of 1 that it will be outside this negligible set, and therefore the preimage will be a manifold, which all of those pictures are explained by this for these smooth function cases. Of course, for Lipschitz we had this diamond, every preimage was a diamond, so the claim fails. Okay. We want to prove this corollary too under the weaker assumptions that f is only Lipschitz rather than ck, where k is at least 1 plus m minus n, which can be a large number if m minus n is large. So one approach So 1. Okay. F failed. This will definitely fail. A failed approach toward proof of this equality star for Lipschitz F. So what is this failed approach? Approximate the Lipschitz function with the C1 function outside a subset of epsilon measure. This we have seen many times, that every Lipschitz function can be approximated, that is, it is actually equal to a C1 function if you subtract a small set from the domain. Then, so do this, then apply the regular CK Morse-Sard to F, to the new F. This fails, this will fail because the CK, k bigger than or equal to 1 plus m minus n, is sharp in Morse-Sard. That means even if you had your f just C1, not even before after approximation, let's say you started with the C1 function, this claim of the Morse-Sard is actually false for this. An amazing example was constructed by Kaufman in so I want to make sure Kaufman has one n. Yes, so in 1979 in a 2-page paper. What he constructed was the following. There exists a function f from R3 into R2 that is C1. Rank of the derivative of f at x is less than or equal to 1, so it's not surjective at every x in R3. And the surprising part, f is surjective. So the particular construction he made was from the cube to the square, and that's why the paper was called a singular map of a cube onto a square. So for reference, a singular map, singular being this rank condition, of a cube onto, that is the keyword, onto a square. So a Morse-Sard here would have required k at least 1 plus 3 minus 2, which is 2. So with C2 you cannot make this example, with C1 you can. And that shows sharpness of the CK assumption in the clearest way possible, in a very compelling way. Okay, so we cannot expect that approach to work because it already fails for C1 maps. What we salvage, though, is what we call weak Sard's theorem. Okay, what is that? Weak Sard's theorem is that, okay, suppose if Rn into Rn is Lipschitz. And A is a subset of this critical set of F. Then this integral Hm minus n F inverse of z intersected with A dln of z is again 0. And it's equivalent to saying that for ln almost every z in Rn, Hm minus n F inverse of z intersected with A is 0. Okay, that is the theorem. So in what sense is this weaker? In the Morse-Sard theorem, where we had CK regularity rather than Lipschitz, we had that this set here is an empty set, which is a much stronger claim than saying that it only has measure 0. For example, a set in R1 can have 0 Lebesgue measure and be uncountable like a counter set. It's way, way bigger than just being empty set. So the usual Morse-Sard under stronger assumptions claims that this set is empty set. The weaker one says that only that its measure is 0. And but also this theorem has weaker assumptions, so it's not fair to really call it weak Sard, but that is kind of a terminology common. Okay, and this will exactly be what we want for Coarea formula, because this will tell us that the Coarea formula holds on the critical set. This is 0, and then Coarea factor is 0, so it's integral of the Coarea factor there. Okay. Now we're going to give a proof of this, very different from the proof in the references I have been giving for the Coarea formula, Federer's book, and Evans and Gary P's book. There they prove the Coarea formula for the regular set where the rank is full, and then they do a perturbation trick to get the case of rank less than n. However, the proof that I'm going to present does not require any knowledge of the Coarea formula. For example, you don't need to know what a Coarea factor is. You don't even need to know there is a Coarea formula. Because look at this statement. It has nothing to do with the Coarea formula. It's all about sizes of the fibers of a map. And it's not claiming that this is equal to integral of some very fine geometric quantity called the Coarea factor. Therefore, it's advantageous to have a proof of this that does not touch on that machinery. And the proof I give you, to be honest with you, is kind of what we have come up with my collaborator, Piotr Hajwasz, and it's going to be published in an upcoming paper of us. And not just for this Euclidean case, we do the same, basically the same proof for maps, Lipschitz maps into arbitrary metric spaces. But the idea of the proof is just as simple and just as geometric. Okay, so here is the theorem and the proof we give. I'm going to give actually all the details. So okay. first and the most important claim is that if x is in A and derivative of f at x exists and rank of that derivative is strictly less than n, then there exists a delta positive such that, so I must actually start with the fixed epsilon positive. So fix that epsilon, and then there exists a delta positive such that for every radius positive and less than delta, the set ball of XR, the image of ball of XR can be covered by n to the power n minus 1 many balls of radius less than a constant which is universal times r divided by n. So here n is just some natural number. Okay, so give me a second. This was too early. Okay, the reason is because I don't have my picture yet. So the idea is to show that if x, derivative of x at, derivative of f at x is less than n, has rank less than n, then image of this ball is smaller than it would have been otherwise. Okay, so the image of the ball under a Lipschitz map can be anything. It doesn't have to be a ball or anything like that. So this is FB XR. So it has a diameter. So diameter of f of ball of XR is less than or equal to Lipschitz constant of f, diameter of the ball you started with. That's always true just by what the Lipschitz function is, and that is L, which will be our name for the Lipschitz f, times 2r, the diameter of the ball. Okay, if you want to, so the diameter of this thing is a multiple of r, so it is order r diameter. If you want to now cover it by sets of diameter this much, for a generic set, how many subsets would you need? So you do a grid of side length r over n, and then there will be r over n. And this grid, each one has diameter comparable to r over n, but how many will we need? We will need, in each coordinate axis direction, we have divided into n many pieces. So we would need, so for a generic set, E inside Rn, we would need n to the power n many subdivisions to break its diameter into capital N many to achieve diameter of E divided by n. sets. Okay, that's for a generic set. But we will show that since rank of derivative f at x is less than n, this f of ball xr, this is our E, is not just any set. It's special, and we will see in what sense. So I have to redo my picture. Here will be my point x, and here goes my function f. So my pictures are like here, you can imagine it's R3 into R2, but in any dimensions it will be basically the same. So here will be f of x. Okay, I want to draw the image of the derivative first. So derivative of f of x is a linear map, so its image will be an affine subspace passing through f of x. So rather, let's see, it doesn't have to pass through the origin. Okay, so this blue affine subspace is the image of the linear map dfx applied to all of our m. Okay, it's a translation of a linear subspace to pass through f of x. So it's a plus f of x. Okay, x is fixed. This blue line is that affine space. And then the image of the ball will be contained, so from above we see that the longest it can get away from f of x is by a multiplication by Lipschitz constant of f. So here will be some part of this affine subspace, which from here to here is at most Lipschitz times r. Okay, so the blue things have to do with the derivative map, which is a linear map. How about f itself? Well, f itself is only a Lipschitz map, and it can be anything. So it can do anything. So the image of the ball is this red thing, which doesn't have to be contained in that affine space. But what is true is the following. F of y minus f of x minus derivative of f of x applied to y minus x divided by norm of y minus x goes to 0 by differentiability. That means there exists this delta positive such that for every y in this delta neighborhood of x, this will be less than epsilon. So we take this epsilon to be 1 over n. So if we take this radius r small enough, we will have this inequality. Now this quantity here is in the affine space, the blue part that we just showed. So this goes to show, and this is at most r, so this goes to show that f of ball x r is contained, so let me write it actually in words, it's easier to see, is contained in r over n neighborhood of the affine space so intersected with ball of f of x and radius Lipschitz times r. So that will be just from here to here. So the red part isn't somewhere here or here. Those are also very close to the affine space. So the whole idea is that the function is just very well approximated by the derivative map. And we know derivative map is contained in this subspace, and this radius of that from here to here. And for every y this is true, so that means it's contained in this neighborhood of that. Now, if we want to cover this red by sets of diameter r over n, we can do better subdivisions. And let me do those subdivisions in green. So along this affine subspace, I cannot do anything. I have to divide. So the diameter is r, L like is a constant, so is order r. To divide into n, I have to divide into n pieces. Okay, but in this other direction parallel to it, I don't need to divide actually. So this is order r over n, which comes from here. It's in the Rn neighborhood of that. Or maybe I do just two divisions, one going up and like from here to here, and then one from here to here. So in how many directions? Here, implicitly, I've assumed that rank of the derivative is actually equal to n minus 1. So derivative is 0 in one direction, or degenerate in, it drops one direction. But if it goes down further, it just helps us. Or you could artificially add, think the biggest ball in n minus 1 dimension, and this same subdivision will work. So the point is that there's at least one direction, in this case going this way, in which you don't need to divide. That's the whole point. Therefore, so how many divisions do you have along the other directions? There are, okay, f of ball xr is contained in, okay, along n minus 1 many directions, I have to divide by n. So I can put a grid of side length n in the subspace of dimension n minus 1. In the other direction, again, you don't divide, or divide only by 2, so it's just a constant, doesn't matter. So this image of the ball, the red part, is contained in n to n minus 1 many balls or sets of diameter comparable to r over capital N. Okay. So these will be kind of the boxes that we make to cover the red set. So the recap will be if derivative of f at x is less than n, then for r small, the image f of bxr can be covered by n to n minus many balls of diameter less than or equal a constant times r over n. So the point is this: instead of n you have that. That means you have saved at least one power here, and you will see how significant that will become. Okay, so at every x you can do that. Then let's do it at every point of the critical set. So suppose A is a subset of critical set, and without loss in generality, because we can work in pieces and then add up, assume that Lebesgue measure of A is finite. That will be a technical thing that we will need. Okay, fix n a natural number. The above is always like for every natural n, you can do this. And fix delta positive. For every x in A, fix ball of x and radius x n. So this radius depends on the point x and also depends on the capital N that you pick, such that image of the claim above holds. So the image of this is contained in union of n to power n minus 1 many balls, which I index like this. So these balls are centered near f of x, if not exactly at f of x. So b1, and then the last one will be bn to n minus 1 f of x. Union of these where diameter of each one of these guys, J, is less than or equal to a constant value Rxn divided by n. Also, these will be, the previous claims were true for R small, so we can assume that all of these Rxn are less than delta for all x and all n. So n is fixed, so just for all x. Okay, because you can always go smaller, so let's say you pick them less than delta. Okay, so back to pictures again. Here is the set A, which lies in the critical set. At every x in A, the rank is less than n, and we have this ball around around the point x with those properties. So for this x, we may have to pick a smaller ball. For this one, even smaller. The ball for this may be containing the previous one, and whatnot. So at every x, we have picked a ball, and in the image, so image of each ball is some set which is contained in union of balls there. Okay. So the ball B x Rx n lives here. The balls B f of x J live here, and they do a covering of, so the union covered this image of the ball at x Rx n. Okay, but there are too many balls going on here. Uncountably many probably, so that's too much. But we have the amazing Vitali's covering theorem. And it's also known as the 5R lemma. And here we apply it to this collection of balls x, R, x, n. We divide by 5, still they cover the set A because every x is just the center of that ball. Gives a countable collection B, x, I, R, I. So here I drop this xn notation and choose the simpler Ri. So there's a countable collection, or maybe finite collection, so let's not write infinity, such that they still cover the set A, but the benefit is that these are in fact disjoint. So Ri over 5 intersection B xi xj rj over 5 is empty if I is not j. So they become disjoint, and if shrunk by scale 5, and their union still covers the set A. So we moved from an arbitrary, possibly uncountable covering to a countable covering. Why we need countable coverings? Because in the definition of Hausdorff measures, we by definition need countable coverings. So the rest of the proof is very, and I mean it, similar to how we proved the Coarea inequality. And it's just such a satisfying proof when all the calculations will work out. So Coarea inequality, remember, it's called the Islenberg's inequality, and we did give a proof in previous video. Okay, so the observation in that proof was that f inverse of z intersected with the set A is covered, of course, by this union of B, X, I, R, I, because they cover all of A, so in particular its subset. But then we said I such that these are relevant for covering of this. So, and when is BI really needed in covering this? That is when f inverse of z intersected with ball of xi r I is actually not empty. If it's empty, that means you don't need bxi r I in the covering of that. And therefore, we can use this covering to estimate the Hausdorff measure of this set. So we are going to measure the Hausdorff measure, to estimate the Hausdorff measure of this. That will be m minus n dimensional. And remember, Hausdorff measures are never found directly, but we need to estimate them. So the coverings we have radius less than delta, so this will be coverings by diameter less than 2 delta. So this is an estimation of this Hausdorff content. So this will be less than the summation of diameters of BI. Let's say I write BI for these to power m minus n. There is the dimensional constant. I have to put w m minus n, so I just put this wiggle thing to mean that there are some universal constants coming in. These universal constants just depend on the Lipschitz constant, the numbers m and n, and maybe that number c, which was how big the coverings of the image balls are. And they do not depend on capital N, they do not depend on delta, so everything will work out. So here, this will be again just the relevant i's. And as in the proof of the Coarea inequality, we saw that there is a clever way of doing this, which i's are relevant. So this will be add up all of diameter BI's. This counting, this part where it checks if BI is relevant or not, is contained in this. So this will be whether the image of BI vanishes, the characteristic function of that vanishes in Z. This is exactly saying when the preimage of Z intersects the ball BI. So this is true for every Z. And so we can integrate both sides. So here's a function of Z, here's another function of Z. therefore the integral inequality will hold. I'm working with the upper integrals, so I don't have to deal with measurability, so this function most probably is not measurable even. So this dln, so I'm integrating these two functions on Rn, is less than or equal to integral of this other side. Okay, and this is wiggly. But those are characteristic functions, so this will become I, diameter of bi to power m minus n. And this would be Lebesgue measure of the set bi, the characteristic function. Now comes the, again, diametric inequality, which gives us a way of comparing the Lebesgue measure to the diameter. Up to a constant, the Lebesgue measure is less than just diameter to power n. This is saying that in Rn, the volume of a ball is just some multiple of diameter of the ball to power n. And balls are the largest in volume among all other sets with the same diameter. So this will be diameter of f of bi to the power n. Okay. We needed some adjustment here, and that was right here. So I stopped checking my notes. Okay, so here I can add this line. So the whole point of this covering of the image of ball was that now we can cover this by union of those balls in the target. And for every I, we had j from 1 to at most n to power n minus 1, many of those. So this will be diameter of bi, which is the same. And this will be characteristic function of, so the ball, so the notation we adopted was ball of f of x and j. So union over j of these balls covered f of bi. So this is, when translated to characteristic function thing, this will be just that. Okay, so this characteristic function is less than summation over j of these characteristic functions. Okay, now, so here instead of this, I'm having actually a ball at f of x j. So this will be diameter of ball f of x j. And now I have summation over I and j. Now the isodiametric. Okay, now we use this fact that so this I j, diameter of bi's or ri to power m minus n. So this is radius, but this wiggly thing contains every constant, that 2 to power m minus n and whatnot. So this is it. Diameter of f of x bj's are comparable to radius divided by n, and then to power n. Okay. Now you see that these quantities are independent of j. Therefore, I do this interior summation. And from that, it becomes that this is I. How many do I have? So this is j from n to at most n minus 1. So this will be n to power n minus 1 many. There is n to power n in the denominator, and then ri to power m when I add up the powers. So this gives you 1 over n, that one extra power that we saved here. And this will be summation over I, or ri to power m. But now I can multiply and divide by 5 to power m, ri to power 5 to power m. Now the point is that these are disjoint balls. They don't have overlaps, and they are contained in a neighborhood of A. So A had Lm measure finite, or we could even say A is like bounded, so that these balls maybe go outside A little bit, but not too far away. But whatever happens, because of the non-overlap, this will be, say, 10 times the Lebesgue measure of the set A. Maybe +1 in case ln of A is 0. Okay, so this we calculated and estimated this quantity here with this value. Now notice that on this side we have no capital N. Here we just computed this quantity. And now here we have this capital N, which is arbitrary. So let capital N go to infinity to deduce that this upper integral h m minus n to delta of f inverse z intersected with a, the ln of z equals 0. Did I do a here? Right. And this means that h m minus n to delta f inverse of z intersection with a is 0 for ln almost every z. But if the content is 0 for any delta, even if delta is equal to infinity, then the Hausdorff measure itself is 0. That's a nice exercise. Probably I've done it in my Hausdorff playlist for ln almost every z. So every time this is 0, this is 0. And that's the end of the story, because if you integrate an almost everywhere function, almost everywhere 0 function, by the way, if a function is 0 almost everywhere, then it is a measurable function. The ln of z. So I don't have to put a upper integral there. So that's the end of the story. What we have shown is that if you are in the critical set of a Lipschitz function, the weaker Sard theorem holds. That means almost every fiber intersects the critical set only along a set of measure 0. Okay, so this was the last important step in the proof of the Coarea formula. So now we have this weak Sard's theorem, which takes care of the critical set. On the other hand, we had the implicit function theorem on the regular set where rank was equal to n. There will be a negligible set where the function is not differentiable, so it doesn't follow any of these two. Then we had the Coarea inequality, which took care of such sets, and also which took care of the measurability of the integrand. And these three are the only things we need to give a proof of the Coarea formula that is quite geometric, explains how and why things work the way they should. Okay, I will explain this proof in the next video. So I bring together all of these ingredients that we have discussed separately. So be on the watch for that. And one way of getting there is to make sure you subscribe so that you will be notified when I upload that video. This was a difficult proof, so sorry for the hiccups. Put your comments, your questions, if there were any parts that needed more clarification, if I made some mistakes, please do consider commenting. I will be very grateful if you gave me feedback, and maybe there will be some interesting questions that will come up and we can discuss later. Until then, have a great one, and thanks for watching this video. By the way, I put the PDFs of all these notes in the descriptions. Not just this video, but all videos. Thanks.